Hi, this is the presentation for Senior Design Group 3. This is the laser beam characterizer. Here we have our setup. We have two layers to it. The laser is right here. We have our collimator here, and the laser is aligned right now to this section here. This section here is what our actual system is. We have these two irises that the user will align the laser to, and then all the alignment for the rest of the system is going to be based on these two irises. Immediately after this, you have a polarimeter here. You have a quarter wave plate and a linear polarizer in here. And the stepper motor here will rotate the quarter wave plate in order to measure the polarization. Immediately after, it goes into this 800 millimeter focal length lens, which will focus the beam. It's redirected with these two mirrors. Then here we have a beam sampler, where it's going to use the Fresnel reflections to sample about 5% of the beam up here and into this Michelson interferometer. Most of our electronics are on here too, so the wiring is a little bit messy, but you can see a beam splitter here in the middle, a mirror here on a stage that can move back and forth, and then we have a detector here that's going to read the interference signal as we move the mirror back and forth. Then if we go back over here, we have 5% that went this way, the rest of it goes over here, and if you can see in here, we now have two mirrors on a stage here that can move back and forth. Our power meter is right here with two fan blades right here that are going to spin to do a knife edge test on the beam for two axes. And then in order to measure the divergence and m² factor of the laser beam, we have this stage to move it along. There's a homing switch here so that the stepper will know exactly where it is. And then we can take all of our measurements that way.
Here are all the electronics for the system. We have our main PCB right here. We have a 12 volt power supply coming in, DC, and this is where our computer interfaces with the board. The power gets broken out into a 3.3 volt regulator and a 5 volt regulator. This is broken out to clean up some noise we were having. We have our three stepper motor drivers, one for the Michelson, one for the quarter wave plate, and one for our translation stage down below. We have a bunch of other boards that interact. We have a dual DC motor driver right here that drives our profiling knife things, knife blades. This is a variable gain TIA controlled digitally and lets us adjust the gain of the TIA to accommodate for different powers of lasers. We also have one more TIA right here for the Michelson that connects directly to the board, and both of these TIAs go into these channels. And then we have one little homing switch on the bottom to tell our translation stage where it is.
For our variable transimpedance amplifier, is used to amplify the power read by the Thor-Labs power meter photodiode. There are 4 gain states to this variable TIA with resistors of 1.3K, 13K, 130K, and 1.3 megohms. This gives a gain of 10x every single stage. So originally, the gain states were wired in series, and the switches would short which resistors were not needed for the gain state. But there was a weird nonlinearity that we saw where in gain stages 2 and 3, there was a huge spike in gain with a small amount of power, and it was really not nonlinear. So this caused us to have to redesign a little bit. And so we rewired these to be in parallel, and it gave us much more consistent results. So at our responsivity at our tested wavelength was about 21.3 milliamps per watt. And so we performed a power versus voltage sweep to determine the transfer function of the TIA. So here are the results that we have. So for stage 1, since the gain is super low, we were limited by the power of our laser, so we only got a few points there. But you can still see a pretty good linear response on all of these stages, and the fit is very well. We calculated the effective feedback resistance of each state, given the known responsivity at our wavelength. With the first stage, it's a little bit This is because of the on resistance of the voltage controlled switch, and all the other ones are consistent.
This is the GUI. It's going to be the main interface between the MCU and our data collection. We have a COM port selected, and it will connect to the MCU. We have 4 different measurement systems: polarization, wavelength, divergence, and M². When selecting each one, you can see the window will change for the graphs for data that will be collected. We have a metric system that's going to show any data collected and also any data results. And then we have a console that will show any changes for mode selection. Once the measurement system is selected and you start the command, it will send it to the MCU and start any motor processing data collection happening.
So here we have our demo for the polarimeter setup. This is a linear polarizer that's just going to set the polarization to around horizontal polarization, depending on how well I could put it there. And then here we have our polarimeter that's going to rotate the quarter wave plate and linear polarizer. So he's going to start it from the GUI.
And at the end, we'll get a plot. Should be horizontal right now, so it's not perfect, but we have the point test here.
So here we have another configuration. We've inserted a quarter wave plate after the linear polarizer to make it a circular polarization, to make sure that we can do different sorts of polarizations. Run it again. Ready to go. So this is our measurement for the divergence. The motor is going to go until it hits this home button, and then it's going to move to the paraxial focus. Paraxial focus is going to be approximately 32 inches away from the lens. The lens is over here though, so it's going to be approximately 32 inches from the lens to the power meter here where the fan blades are going. So you can see it's almost there. We're having some issues with our stepper motor. It's being really loud right now. I think it's just bend in the stage screw. So it's going to go till it hits the button, and then it moves. So now it's homed, and it's going to move back to where the paraxial focus is. From here, it's around 5.5 inches this way till it gets to paraxial focus. So here it stopped, and then now immediately it starts beam profiling there. The beam profile for this that it gets is going to get approximately 10 of them to average them for each axis. And the divergence of the beam prior to the lens, before it goes, the laser goes into the system, is going to be this beam width divided by the focal length of the lens. Now, our beam widths have been super noisy despite our calculated good resolution. According to our calculations, we should have 9 micron resolution since we're doing this based on the encoder counts of our DC motor. But despite this, we've had a ton of noise that we haven't been able to really get around yet.
So it's going to do 10 90-degree scans. Now some of these aren't going to be perfect good scans, so it's going to exclude some of these. That's why sometimes it might go a little bit more than 10 scans. So here it switched axes, now it's doing the other one.
So these are some of our beam profiling results and some issues that we've been having with them. So right now with the beam profile, we are doing a knife edge scan with a DC motor running on 2 axes, running at the 10 RPM. And we should be getting a knife edge scan as seen in that top left corner picture. We do a smoothing filter with the power that's encoder count based. And then we are doing a smoothing filter on that, and then we're putting it to an error function to get that yellow line that you see to develop power, which is the blue one. And we find our T naught from that. So far that's been good, but we've been having some issues with our resolution, which should be 9 microns, but we haven't been getting that during our results. And then you can see on the right that we have our summary of our scans that are based on 10 scans per axis on one position of the translation stage. And it will filter out any invalid scans based on low power or if there's like a huge spike in power for a gain stage. And then you can see on the bottom left our Z position versus beam width graph. That's why we see those dips of what should not be there due to our bad resolution from the ADC.
So here we have our Michelson interferometer. You can see the mirror on the left moving back and forth. The beam splitter is right here in the middle. Yeah, here we go. And then we have a stationary mirror here. The laser comes through here, and then we have our photodetector here. It's a photodiode with a transimpedance amplifier. The mirror is moving at 10 millimeters per second. And when we see the output on the oscilloscope, we can see that as the mirror moves, we see a frequency. And there's an approximate frequency of 9.7 kilohertz right there on that spike there when you take the FFT of the data. And doing the math, this comes out to a wavelength of around 2.05 microns, which is only 1 nanometer off from the actual wavelength of the laser. Here is the demo for a microsync interferometer. You can see the mirror moves back and forth. It doesn't need to move a whole lot. We can see the results are extremely noisy on here, despite them being really clean on the oscilloscope. We're not really sure where this noise is coming from, but this is where we're at so far. So just a quick overview of the problems and troubleshooting that we've had to do. The main problem we've had is just time. Because of just sponsorship issues, there was a lot of delays in getting hardware, so we didn't get any of our major hardware until second, third week of March. So we've been on a serious time crunch for this project. With this delayed, we have a ton of software development required for this project. And so because of that hardware delay, we're super delayed with software as well. Most of everything is like completed. It's just working out lots of different little kinks and stuff. We've had noise issues, as was discussed earlier, with beam profiling. Even though we should have, in theory, a 9 micron resolution of our beam profile, we're getting huge variance on our beam profiles, which is making it really hard to get any good measurements. Additionally, we also have noise in the mics and interferometer signal, which is where we can see it very cleanly on the oscilloscope, but when we put it on our SDM, even though we're doing very similar noise filtering algorithms, stuff like that, we're still having issues actually reading the signal. We're not super sure of the noise source, if it's the ADC or just general electrical noise, if it's the motors. We're not 100% sure. We haven't had a ton of time to really explore that. We've also had some issues with the gain switching, creates spikes, and so sometimes it doesn't really cause a huge issue, but sometimes it does come out and mess up with the data, especially in the beam profiling. So we're trying to filter that out, but we kind of ran out of time on that. And then the data, we've had some issues with data streaming, but it's mostly resolved. And sometimes that does lead to getting invalid beam profiling scans. But this is just a quick overview of what we've been through, and some of the issues we've been having.